motion of an object that is thrown and models projectile motion, and compared the observed trajectory of the object versus a computational model which only accounts for gravity versus a computational model which accounts for both gravity and drag force. So the models used, the object thrown was a wadded up piece of paper. The location was on a table on Earth with mirror 6 calibrate. The observed model was created using tracker, and the computational models were created using GlowScript. So some physical principles, we have Newton's second law, which states that the force of an object is equal to the rate of change in the momentum with respect to a change of time, also known as F net equals dp to dt. And we can use that formula to derive the velocity update formula, which will be used in the computational part of this experiment. And another formula used in the computational part of the experiment is the position update formula, which is derived from the velocity average formula. And so more physical principles, we have the force of gravity. So the acceleration due to gravity on Earth is negative 9.8 meters per second squared. And the force of gravity as a unit vector, as a vector is 0, negative mg 0, where m is the mass of the object in kilograms and g is the acceleration due to gravity. And then we also have the drag force. The drag force is equal to negative bv squared times the unit vector, and b is a constant, and which is experimentally determined, and then the drag force acts in the opposite direction of the motion of an object. So the experiment, the system was the paper ball, the surroundings was everything else. We threw a wadded up ball of paper like a basketball to model projectile motion. The motion should be two-dimensional across the screen. Import the video in the tracker, put the x-axis on the table and the origin below the initial position of the object. Construct a computation model with the GlowScript starter code and edit the code as needed to align with the observed model. The first computational model should be with only gravity acting on the system, while the second should include both gravity and drag force acting on the system. And lastly, compare the data of all three models graphically. So here's our observed model. As you can see, it was used with tracker, and the ball was thrown like a basketball with 2 mirror sticks to calibrate. So from the observed model, we get our initial data. So the initial velocity was 1.895, negative 1.0020 meters per second. Our initial position was negative 4.85, 1.0440 meters. The initial time was 0 seconds. The delta t was 0.0333 seconds, and the mass of the ball's mass because was 0.0045 kilograms because it was just one sheet of paper. And so we plugged this data into the computational model. We plugged the mass in. We plugged in the data for the position vector and velocity vector and updated the time in delta t. We set the magnitude of the acceleration due to gravity to 9.8, and I guessed and checked to find the proportionality constant for the drag force, and I ended up deciding that the B was 0.002, but please note that for the first model, where there's no drag, only gravity, B is equal to 0. Because when we plug it into this part of the code, we set the t time to equal to the time ran for the observed model. V hat is equal to ball dot velocity divided by the magnitude of velocity. And then we put the force of gravity vector from earlier as stated earlier, and update the drag using the formula derived earlier. And then F net is equal to the force of gravity plus the force of drag force. And then we updated the ball's velocity and ball's position using the formulas stated earlier. So from the computational model, this is the graphs derived from the computational model with both drag and gravity. And as you can see, the drag causes the velocity to not be constant in both the x and y direction. So for a graphical comparison, we have the green, which is the computational model with gravity only. We have the blue, which is the observed model, and the orange, which is the computational model with gravity and drag. And as you can see, for the y positions of the computational model with gravity and drag and the observed model line up more closely, and their overall shape seems to be more similar, but there is a clear difference in the x position, as the x positions of the computational model with gravity only and the observed model seem to align more closely. So some possible errors: human error, center and mass point could have been off when using tracker. The ball center mass, it was a wadded up paper ball, so it doesn't have a perfectly uniform center and mass, so the motion might not be a perfect representation of projectile motion. And then rounding, the time was 0.0333 repeating, and so decimal places could have resulted in slight deviations between models. So further questions uh, about the terminal velocity. Was there terminal velocity? And if no, how could we show terminal velocity? So the models do not reach terminal velocity because in order to reach terminal velocity, the net force has to be zero. And as you can see from the graph with both of the of the computational model with drag and gravity, the slope is not linear. And if or it does, it's not a constant slope, and because it's not a constant slope, there's no terminal velocity. And so, an experiment to make the terminal velocity would be allow dropping it from a higher distance to allow air resistance to equal gravity. And then if it was straight up, how would the time differ? The time would be longer because all the velocity would be in the vertical component, which would cause me more speed in the vertical, a longer time for it to decelerate to become zero. And yeah, thank you.